CH4 is an easy molecule, you guys can do that. CH2F2 also you can do. In fact, we do have a molecule drawn here for CH2F2. So this one right there. So you can draw that also. It's not that hard. Ammonia molecule also we have drawn in many instances. So you can draw ammonia molecule too. And water, it's a good molecule for you to know how to draw. So you can try that. And BF3 is also not that hard, you can do that. And C2H4 excuse me, also not a difficult molecule to draw. You put the two carbons bonded to each other, and then each carbon will have 3 hydrogens in it. Okay, and since there are 2 carbons and they are symmetrical, doesn't matter which carbon you pick to find out the electronic geometry or the molecular geometry. Okay, always you look one central atom at a time when you are finding the electronic geometry, molecular geometry, or the hybridization. Now let's do C2H4. So when you draw C2H4, it would be like this. You can follow the rules for how to draw the Lewis structure. First count the number of valence electrons, get the skeleton, and then put 2 electrons for each bond, and then the remaining you put as to complete the octet in the outer atoms first. Okay, now this is C2H4. We want to find out the electronic geometry, right? That's the first thing. Yeah, electron domain geometry. Now there are 2 carbon atoms, so you can look at 1 carbon first. If you look at this one, electron domain geometry, how many electron groups are surrounding this carbon? So this is 1 group, 2 group, double bond considered as and 1 group. So there are 3 electron groups. So if it is 3 electron groups, what is the electron domain geometry? So the 3 electron groups would be, you can refer to the table. I'll show you how to find out. So the 3 electron groups, 3 electron groups, right? And then all of them are bonds. So the hybridization is going to be sp2, and then the electronic geometry trigonal planar, molecular geometry also trigonal planar, when you have 3 electron groups and all 3 of them are bonds, no lone pairs. Okay, so this one, electronic geometry is trigonal planar. Trigonal planar. And then the molecular geometry also would be trigonal planar. Molecular geometry. Trigonal planar. And then the next thing is hybridization. When you have 3 electron groups, you can refer to the chart, that is sp2, polar or non-polar. Now this one, between carbon and hydrogen, bonds are non-polar. There is no electronegativity difference between the atoms to make it polar. So this would become a non-polar molecule. Non-polar. Okay, and then the C2H2. Now you know how to draw C2H4. You can draw C2H2. You will find there is a triple bond between the 2 carbons. Okay, so try to do that. And carbon dioxide also is already given, the carbon dioxide molecule, in this handout, one of the previous pages. You can see that. And then the sulfur dioxide, you can try sulfur dioxide, SO2. It's not a difficult molecule to draw. Do you want me to show it to you? Okay, let's do it then. So sulfur, see, remember how to calculate the number of valence electrons. So sulfur, group number is 6, and oxygen, there are 2 oxygens. So group number is 6 times 2 is 12. So there are 18 valence electrons. So when you are drawing the Lewis structure, we use that 8 electrons to draw the Lewis structure. So sulfur going to be in the center, always the least electronegative element going to be in the center. and then you put your 2 atoms. Okay, and then for this is a skeleton, so we have to make bonds between the atoms. So out of the 18 we use 2 for the bonds, so we are left with 14 more. So that 14 you put to giving 8 electrons. You first go for the terminal atoms. So now put 12 electrons right there. So how many more left now? 2 electrons left. And then you put that 2 over here. Okay. Now let's see. After you draw the structure like that, you can see that the sulfur has only 6 electrons. Do you see that? Oxygen has 8. Oxygen has 8 electrons, shared electrons, but the sulfur has only 6. So what we can do is we can put a lone pair to get rid of that sulfur. 6. Okay. So if you put a lone pair, you take one of the oxygen lone pairs and then you put it as a double bond. So that made sulfur 2468. And then after you do that, you're going to check to see if the atoms has any formal charges. Remember how to calculate the formal charge? Formal charge is calculated. Group number, let's look at the sulfur. What's the group number for the sulfur? 6. Minus the number of electrons and bonds on the sulfur. There are 3 bonds and then has 2 electrons on the sulfur. So 6 minus 5, that is plus 1. So sulfur formal charge is plus 1. Let's look at oxygen. Oxygen group number is 6 minus, it has 1, 2, 3, 4, 5, 6 lone electrons and 1 bond. 6 plus 1, 7. So 6 minus 7 is minus 1. So sulfur plus 1, oxygen minus 1. There are formal charges. Let's see if we can minimize the formal charges. Okay, how do we minimize? Whenever if you come across that there is a plus 1 and a minus 1 charges next to each other, you can make another bond and get rid of that formal charges. So basically what we can do is we can take one of the lone pairs on oxygen and then we can put a bond like that. Now after you do that, let's calculate the formal charges. Now oxygen group number is 6. Now it has 4 electrons and 2 bonds. 6 minus 6, 0. And then the sulfur group number 6, it has 2 electrons and 1, 2, 3, 4 bonds. So 6 minus 6, 0. So now by doing that, sulfur and oxygen both formal charges 0. So the correct Lewis structure for sulfur dioxide is this. Okay. Okay, that's the correct structure for sulfur dioxide. And then what's the electronic geometry? Well, you're going to look at how many groups, electron groups are on sulfur. So this is one group, 1, 2, 3. So there are 3 electron groups. So if when you have 3 electron groups, the electronic geometry is going to be trigonal planar. Trigonal planar. And how do we find out the shape of the molecule? So we can refer to your chart, trigonal planar. When you have 3 electron groups, trigonal planar with a 1 lone pair over here on this line. You see hybridization sp2, trigonal planar. What is the shape of the molecule? The shape of the molecule is going to be bent. Molecular geometry would be bent. Okay, that's how you find molecular geometry. So it's going to be bent. This is going to be bent. And the hybridization is going to be 3 groups, sp2, and then the polar. So between sulfur and oxygen, oxygen is more polar, so there is a bond polarity. Okay, so the bond polarities will not get cancelled because of the bent shape. So as a result, SO2 will become a polar molecule. It's a polar molecule. Okay, and then XeF4. Again, you can draw the molecule with the same method that we just talked about, XeF4. Draw it yourself and see what you're gonna get. Okay, and then SeF6, BrF3. SeF6 also, I think you should be able to draw it without any trouble. BrF3 also you can draw. XeF2. Let's do XeF2 then. So let's see. Xe. It's in the group 8, valence electrons 8, and F2, there are 2 fluorines. 2 times 7, 14. 14 plus 8. Xe is in the group 8. So how much is going to be 14 plus 8? 22. 22. So there are 22 valence electrons. Okay, so who is going to be in the center? Xe and F, and then you use 2 bonds, so meaning 4 electrons used for the bonds, and how many more left? 18 electrons left. So the 18 electrons are distributed among fluorine first to give them 8 electrons. So you draw it like this. Now you used up 12. How many more left? 6 left. 6 more electrons left. Now what are you going to do with that 6? You're going to put it on xenon. So as lone pairs. 1, 2, 6. There are 3 lone pairs on Xe. So that is the Lewis structure. And then you're going to find out what is the electronic geometry. To find out the electronic geometry, we need to know how many electron groups are around xenon. How many electron groups are there? How many? So this is 1. We always look at the central atom. Okay, always look at the central atom. So the central atom is Xe. There's 1 group, 2 group, 3, 4, 5. So there are 5 electron groups. When you have 5 electron groups, what's going to be the electronic geometry? You can always refer to this chart. 5 electron groups. You see 5 electron groups. When you have 5 electron groups, it's going to be electronic geometry trigonal bipyramidal. Now we do have a 5 electron group with 3 lone pairs. So that means it's this line over here. Okay, 5 electron groups with 3 lone pairs. They take this equatorial position. So it's coming from the electronic geometry trigonal bipyramidal. So the molecular geometry is going to be linear. Okay, so that's how you find it out. So this electronic domain geometry would be trigonal bipyramidal, and then the molecular geometry would be linear. And then the hybridization for 5 groups is going to be sp3d. And then the polar, what do you think about the polarity? So fluorine is more polar compared to xenon. So in this molecule, you will see polar bonds. Okay, Xe in the center, fluorine, right? So here there is a bond polarity. Fluorine would be more polar. but it is symmetrical, it is linear, and these are 3 lone pairs. They are in the equatorial position. So as a result, bond polarities will get cancelled. The molecule will become non-polar. Okay, this is a non-polar molecule. Non-polar. Okay. NH4 plus ion, you can also draw the Lewis structure. You know that if it is a cation like a +1, how do we make up a cation? By losing an electron. So for the number of valence electrons, once you get it, you subtract 1. And if it is a negative ion, since negative charges are formed by gaining an electron, so once you calculate the valence electrons, you will add 1 electron if it is -1, add 2 electrons if it is a -2 ion. Okay, ammonium ion you can do, hydronium ion also you can do, PF6 also you can do without any trouble, XeF3, that also you should be able to do now that we do XeF2. Okay, so but let's see, I'll do one here with you. Let's do hydronium ion, H3O plus. Okay, so hydronium ion, H3O plus, there are 3 hydrogens, 3 electrons, 1 oxygen, 6, and for the +1, so this one is 6 plus 3, 9, +1 meaning you are making a cation by removing an electron, so you subtract 1. So the total number of valence electrons are 8. Oxygen going to be in the center, and then you put 3 hydrogens on oxygen, and for that we put 6 electrons, each bond carrying 2, so you are left with 2 more electrons. You put it on oxygen, and then the plus charge going to be on the oxygen, +1. How do you get that +1? Remember, that's the formal charge. Group number for oxygen is 6 minus the number of electrons on oxygen 2 plus the number of bonds 3, so 6 minus 5 plus 1, so the oxygen formal charge is +1. That's why hydronium ion has a +1 charge. Okay, and for hydronium ion, let's see electronic geometry. What's the electronic geometry for the hydronium ion? How many electron groups are there? So this is one group, and then with the 3 bonds there are 4 groups. So when you have 4 groups, what's going to be the electronic geometry? That's going to be tetrahedral. Tetrahedral. And what about the molecular geometry? You can refer to the chart. When you have a tetrahedral electronic geometry with a 1 lone pair, that's going to be trigonal pyramidal. Pyramidal. And then the hybridization, when you have 3 groups, that's going to be sp3. And then the polar, yes it does, it is polar, oxygen is more polar, there is a bond polarity like that. And then the molecule will have a net dipole moment, so it's polar, yes it is polar. Okay, so we can do that. And then the resonance structures. We talk about resonance structures at the beginning, that you can change the position of the lone pairs and a pi bond without changing the atom places. Okay, so if you draw the Lewis structure for NO2 minus, it would be like this: nitrogen, oxygen, like that. So this is the Lewis structure for NO2 minus. And then if you want to draw another resonance structure, so the resonance, to indicate, you use this arrow. So now you can change the position of the pi bond. Okay, so basically one of the lone pairs can go to form a bond, and then the pi bond of the other bond breaks and give its 2 electrons to this oxygen. Okay, so then you can draw something like that. So these are the resonance structures, the 2 resonance structures. Okay, I was not planning to draw this one. It's okay, you can draw it. Okay, and then similarly, and you can also write down the electronic domain geometry. What's the electron domain geometry? There are 3 groups. Then you know when you have 3 groups, it's going to be trigonal planar, molecular geometry going to be bent because it's a bent shape. Hybridization for 3 groups would be sp2. So SO3 2 minus. Now that you know how to draw the Lewis structure, you can draw SO3 2 minus, and you can draw 3 resonance structures for that. And for the ozone, there are 2 resonance structures. We drew that in the lecture slides also. Even if you are not in the lecture with me, we can still draw the ozone molecule. Okay, so that's what you need. I would like to see how you guys are going to complete this handout yourself, the ones that I have not gone with you. I'm sure you'll be able to do it, but if you do have any questions, feel free to email me. Okay then, bye for now.